Hi, and welcome to JEY Labs. This is Doug K6JEY. And today we're going to have a little get together about receiver optimization. Basically, it's not just the single item, but the entire receive system from where the antenna connects, feed line connects to the antenna to the speaker. We're going to review equipment, techniques, and some little known items later on. Okay, so let's get started. Receiver system signal noise ratio optimization. And really optimization is about a signal noise ratio. In most professional systems, that's what they look at. Okay, let's see if we can get, sorry. So these are techniques used for optimizing receiver system. It reveals problems with interstage gain compression, receiver sensitivity. It optimizes noise figure, measures audio distortion in the receiver, and reveals cable losses, depending on which technique you use. Let's start with some definition. Noise figure is a relative dB measurement of RF signals using a hot and cold source to excite a receiver chain. It requires a source and a detector indicator unit. And they're fairly specialized, but they're not unknown or unobtainable. SINAD is a measurement that's been around for a long time, mainly used by FM folks. And it has some very specific definition, but basically, it's the opposite of harmonic distortion. You use the 1 kilohertz tone injected into the radio, you null it out and get a residual noise. And in the SINAD measurement, you look for 12 dB signal to noise ratio. And as you change the receiver and align it, you change the signal generator. So it's always like 0.5 microvolts at 12 dB SINAD. In signal to noise ratio, it's simply a dB ratio between two things: the signal, which is the 1 kilohertz tone that's modulated onto the carrier, and the noise. And that's a fairly straightforward measurement. So the equipment you need is a RF generator for the system tested. It should be in the same frequency range, and it should be able to modulate the carrier with a 1 kilohertz tone with either an external audio generator, an audio setup, or internal to the source. And you need a distortion meter or a signal to noise meter or indicator. So 3 pieces of gear. So here's some examples of the equipment. And first of all is the RF sources. If you want to go the whole thing, get something like a Gigatronics 6082A. It goes from actually 0 to 2 gigahertz. It's highly calibrated. It tests itself when you turn it on. There's an internal power meter and an internal frequency counter that lets you know exactly what's wrong, if anything. It has a knob on the front to tune the frequency or output. The attenuator is extremely good, and the frequency stability, of course, is excellent. It has internal FM and AM modulators that can be tuned to almost any frequency that you'd normally use. Or if you're on 1296 and just want to do distortion measurements, you could use one of these old Klystron signal generators. They aren't much for frequency stability, but they are good for output attenuation and modulation. And I bet you could borrow or take one home for free, and the previous owner would be ecstatic. Klystron. When was the last time you used a Klystron? Or if you're going to do HF work, or use the harmonics of a low frequency signal generator, it's hard to go wrong with a URM25. Well, yeah, okay. I've had a lot of URM25s, and they're pretty nice little generators. They're cheap and easy, and they work well. And they have a 1 kC modulated tone they can put on the carrier, and it has a good output attenuator. There's other ways to do it, though. You could use a signal source with no modulation ability and use an RF mixer or a PIN diode as a mixer modulator. And if you have a signal source that's half the frequency, you could use the harmonics, just as long as the 1 kC tone was still readable in the receiver. And here's an example. I used my RF Explorer signal generator and run it into a mixer. I had a Watkins Johnson 4 gigahertz mixer. The generator went into the LO port. The mixer went into the IF port, and the signal comes out on the generator's frequency, modulated with a 1 kilohertz tone on the other port. And then you put whatever attenuation you want on it to arrive at a good signal. You may already have all that stuff. Just put it all together and adjust the levels, and you've got yourself a pretty fair signal generator, really. And it's battery operated and it's portable. It isn't 60 pounds. And there's a lot to be said for that. Well, I just stuck this in because it's just so extravagant. Here's a leader audio tester. It's got a audio signal generator on the right side from 20 to 200 kilohertz. The level settable and the frequency is has quite good resolution. So you could use that as your 1 kC modulation source. But this little critter has a secret. If you notice on the left side, there are 2 meter pointers. One's for the left channel and one's for the right channel. And the 2 channels can be coupled together by pushing the knob in or decoupled to run at different levels. And both needles are concentric on their pivots. I don't know how they did it. I do not have the guts to take this thing apart and satisfy my curiosity. It's ruined more radios. But I thought this was interesting to see. If you run across one, for goodness sakes, get it, because nobody knows what they are, and they're a really unique instrument. Well, if we're going to go into distortion analyzers, and now we're still talking about equipment, it's hard to go wrong with a Heathkit. What, you say, a Heathkit? Yep, Heathkit made a whole string of distortion analyzers. The first group was the manual harmonic distortion analyzers, HD1, the IM58. They all look the same, have the same knobs on them. There's a big blue one that's kind of low and wide, but they also make an intermodulation distortion analyzer. And for our purposes, you don't want one of those. You want a harmonic distortion analyzer. And it's pretty simple. If you look at the knobs, inputs on the left on the banana plugs, there's a volume level on it, off on switch above that. And then you have range. And you put the far right knob in set mode, and you bring the level up so the meter indicates full scale. And then you tune the audio generator, the filter part of it, with these 2 knobs and bring it up to like 1 kilohertz. And then you flip this over to reading at 1 kilohertz. What it does is it nulls out the 1 kilohertz signal, and you're left with just the noise, just the distortion. And you have to how would you say, peak the null, maximize the null with this knob, and then do a little extra with this knob, and you read the distortion. At real low levels, like 1% and below, that may drift around a little bit, so the meter gets a tiny bit fiddly in the lowest ranges. But I've used this for many years for many projects, and it gives good readings. It's cheap, it's available, and nobody knows what they're for. Here's a leader distortion analyzer, an LDM 171, really pretty instrument. Leader always makes nice stuff like that dual pointer audio meter. This runs the same way. You set the level, and then you punch in a distortion, and you go up and down the buttons until you get the proper distortion. The last 3 ranges are automatic. And what it does is it auto-tunes the null, so it stays centered in the null, and that saves a lot of fiddling. But the leader has a nice big meter on it, and it's really quite a pretty piece of gear. Here's an automatic analyzer. You simply put the signal in the input, punch a couple of buttons in general, the thing will go red light, green light, and read the distortion. And these are actually fairly cheap. A full automatic distortion analyzer, I think it's a little over the top, but that's up to you. Oh, no, over the top? No, did I say that? No, here's over the top. The 476D1 by Collins. It's a harmonic and an intermodulation distortion analyzer for receivers and transmitters for the high frequency band. It weighs 150 pounds. It has more transformers than you own inside of it, and a bunch of crystal filters, more than you probably own inside of it. I had one for a while. It just simply was too much. But if you're a Collins collector and you want the ultimate in test equipment, by golly, it'd be hard to beat with one of these distortion analyzers. And the book was available. Oh, okay, now let's go down to the ridiculous. You go from that down to the Cynator, a ubiquitous instrument that seems mysterious, but it's not. It measures SINAD based on 12 dB of signal noise ratio. So you hook this up to the speaker and you put your signal generator into the input, and you, with a 1 kC tone, and you run it up until you get 12 dB SINAD with a level. You'll see when it tunes in. And of course, there are lovely instructions that are available online. And as you adjust the receiver, you increase or decrease the level of the signal generator, and it gives you a level at 12 dB SINAD. And the FM guys swear by this. And it works on FM or AM, and very simple to use. And they're generally inexpensive. I would look for one that was inexpensive. The circuit's very simple. It's just a notch filter and some op amps. Here's a specialized piece of gear. If you have one of these, you are lucky. I know 2 guys that have them. They're Sanders system noise figure meter. So you put the noise source up at the antenna going into the feed line, and you put the Sanders on video at the speaker, and you read the noise figure of the entire system. Almost every radio astronomy observatory uses something like this. They'll do a reading from some stellar object or galactic object, and they'll switch over to the noise head and read the noise figure of the system and calibrate it to that. So every reading they get is calibrated based on the noise figure of the system. And yes, 200 gigahertz, they all the way down to 40 megahertz. That's the way they keep their radio telescopes calibrated, is by doing a system noise figure with a system something like this. Yeah, Sanders is fairly old. If you find one, you can use any noise head you want with it. It'll do 5, 10, and 5, 15, and 25 dB ENR noise heads. So it'll accommodate almost any noise figure, in case, even if you want to make one yourself, but it won't be calibrated. If you're only using it to adjust the relative performance of the receiver, a highly calibrated noise source is not necessary. Okay. Let's see. Oh, here's another way. I worked in an audio wireless microphone customer service support center for a while as a manager. And one of the ways that we adjusted FM systems was to put the same 1 kilohertz tone into the carrier, and then look at the audio output with the vertical displacement stretched out as far as you can, so that the vertical is 10 times the size of the screen. And you look at the loop in the bottom, and you can see in this one there's fuzz on it. Well, that's distortion. So you normally would adjust an FM system for best quieting. In this case, the level of quieting is reflected in the amount of fuzz on the loop. So it's very obvious when you get the thing nulled down just right. There's a very simple, inexpensive way, just using an oscilloscope and a signal generator, to do best quieting or least distortion. Interesting, huh? Here's my favorite. It's made by Comm Spec, and it's a computer program. It's a harmonic distortion analyzer that'll do signal noise ratio and SINAD and total harmonic distortion as a program. And you do the same thing. You get a signal generator, modulate it with 1 kilohertz, send it into here. Oh, I'm sorry. This program has a 1 kilohertz output, audio output, to modulate your signal generator if you need that. There's only one trick in the whole thing. Up here in the top left corner is a power button on a software program. If you don't push that, it won't work. Now you're going to say, I'm stupid saying that, but you're going to download the program and you're going to use it. And you're going to go, why won't the thing work? And my voice should come back to you saying, turn it on. Okay, so the mode will go between different modes. The mixer picks out whatever input device you want to have, and it has a spectrum analyzer from 0 to about 5 or 10 kilohertz, depending on how you set it. And it allows you to see where the noise is and where the harmonics are. It's very spiffy. You will really like it. It's $39 for hams. A ham wrote the program. It gives us half off on the program, but it is only for one computer. You can maybe 2. So don't just install it and everything expect it to work. It's really for one computer. So pick the one you want to use as your harmonic distortion analyzer. I ran into something that I thought was important with it, and that was that I used my Creative Sounds Sound Blaster X Model 3 or whatever the stupid thing is as an external sound card to feed audio into this. And the blaster has a 24-bit 96 kilohertz DAC in it, and they're about $24. It incidentally produces magnificent audio out of your laptop. If you want to listen to music or television or whatever, it's stupendous. There are other DACs. You can get one for $5, but this one makes a difference. So to me, it's worth, as long as you're going to go with the CommTech and spend $39, spend the extra 24 and get one of these. You'll find it's very, very useful. For way up there in the heights type of USB sound cards, the Dragonfly is better, but not by very much, and not by much considering the price. And there's other ways, but the DAC is a way to go, and it makes that CommTech work better. Okay, so let's see what kind of system test setups we can put together. So I used a 1 kilohertz modulation on a signal generator. This was for my 1296 EME station. So I put together all of the coax and relays for the receiver, which is a ICOM 9700, a second preamp, and all of the measurements were done audio output. So with the internal preamp of the 9700 either on or off. So everything was strung out the way it would be on the actual station, including coax, but it allowed me to test the entire system to see what the noise figure was. And here it is laid out on the bench, same bench I'm sitting at. There's a 9700A, and it goes out through some attenuators to a preamp, a G4 DDK, and here's a little lab antenna. And that's listening to the signal generator, which is behind me from where I'm taking the picture, about 4 or 5 feet away. I found if I just went direct to direct, there wasn't enough noise, band noise, to do a good measurement. So by going antenna to antenna, you've got a higher noise floor. If you just go to the receiver, it's so quiet that you don't have anything to work with. So this is set up with a CommTech at 1 kilohertz, and you can see the reading there is like 15 dB signal to noise ratio, and very easy to set up and very easy to test. If I got the signal level and the noise very close to each other, 12 or 15 dB apart. So what happened was any adjustment I made or any connector I changed made a difference in the reading, and that's kind of where you want to tune the system to. So if you change something, length of the coax or whatever, or knock a few dB in with the attenuators, you're going to see a change in the signal noise ratio. Once you're at that sensitivity level, then you can test the entire system A to Z, and you can test preamps. You won't get an objective a number on the preamp, but you will see the difference between preamps. Okay. Here it is hooked up with the KX3. Just, I don't know, I wanted to give you more detail. You can see the Comm Spec is indicating something like 65 dB SNR and the little spectrum analyzer. It's pretty cool. So techniques and equipment used to adjust system for best signal to noise ratio. So you set it up pretty much like we did for everything else. So again, you use antennas. I found a good adjustment range. If I got the signal level down and the gain up to where I got about 65%, 0.65 distortion to 0.15, it's about half the meter scale. I talked about the sensitivity of the measurement. Yeah, if you bring the set level down and the noise level up, you get 0.15 to 0.65 range of signal to noise ratio to work with, and it's relative numbers. It's not, you can turn it into objective, but what you want to see is have the thing change, and that happens when you lower the set voltage and raise the noise level. Okay. And the ICOM's in the AM mode. You can do the whole test in FM if you want to, but AM, that was for AM. You can also do signal noise ratio by ear. And one of the things we do in microwave quite a lot is we'll listen to the compression. Like if you've got too hot of a preamp and overloads the system, you can hear that by ear. You don't get the same differences in signals. And your S meter will move up like S9 noise level. And that's probably not a real good level to run your radio on in the past. In radios like the FT 790s, 290s, 290R, the older radios, the ICOM 736 radios and all that, the front ends are the dual gate MOSFETs, 3SK51, that kind of thing. And those little guys overload really easily. So if you feed too much RF signal in from the converter into the radio, you'll overload it in a heartbeat. I need to tell you that the 7900 was almost impossible to overload. It's a tremendous radio. It's night and day. And you've got the same problem with the FT817. You've basically got a dual gate MOSFET in the front end. And as soon as you get signal levels up, the thing starts to fall apart in terms of operation for exactly the same reason. Okay, here's what I found with the 97 that I thought was interesting. I think the noise reduction in the DSP uses spectral subtraction. It's a new form of DSP, and it's quite different. In actual testing, and this is from VA7OJ's test report on the 9700, here's the improvement in SINAD dB signal to noise ratio with the settings. If you just turn it on, it gives you 6 dB signal to noise ratio improvement. What do you need to do in your microwave system to get an extra 6 dB? A lot. Well, this will go all the way up to 10, 15, 17 dB noise reduction. 4 and 5 is about the most I wanted to do before I got artifacts in it. But at 6 and 8 dB, it sounded like a regular signal, except it was quiet. I was out doing the 10 gigahertz contest last year and used the 9700. And there was somebody up in the valley, San Joaquin Valley, that was really weak on sideband. I pushed in the noise reduction, bang, completely copyable. I'm sorry to go on bragging about the 9700, but it's quite a radio. Another system improvement you can make that goes back to the 1980s for me is that if your radio uses point contact diodes in the product detector in the receiver, like any of the older Kenwood Yaesu ICOM radios, you look at the schematic and you get down to the product detector that turns out the audio. If that's got 4 1N60 diodes in it, change them to Schottky diodes, like the 5082 2800 series or 2900 series. Here's why. At 1 kilohertz, the distortion is about 1% in a radio, in a typical radio with point contact diodes in the product detector. But if you go down to 400 hertz or 300 hertz, the distortion goes up to 30%. Because the corner frequency of the diode basically gives up below a certain frequency. With Schottky diodes, they're used in radar speed guns. And because they're used for Doppler systems, it has to be efficient and clean down to 0 hertz. So that's the way those Schottky diodes are made. The 2900s are better diodes and worth the extra money. All the Drake line, all the way up through the TR7, but not the TR7A. It uses an integrated circuit for product detector. But everything below that, down to the 1A, all uses 2 or 4 regular point contact diodes, and they have a miserable product detector. You don't notice it because you've never heard one without it. Put 2 Schottky diodes in there, you'll have a different radio. Kenwood TS 820, 520, 440, 120, 180, up, I think the 440 may have an integrated circuit, but it may also instead, I can't remember, have point contact diodes. Get in there and pull them out and put in Schottky diodes. It makes a huge difference. Your distortion goes from 30% down to 1%. And what happens is the background noise is soft. You don't realize how raspy and irritating the background noise is until you change the diodes, and it's smooth. Okay. Okay. So look over the talk. This will be on YouTube. Pick a method that suits your equipment and experiment. I like signal to noise ratio. I like the CommTech. You may have some kind of crazy distortion analyzer at home. You want to use that. That's fine. Experiment with it. I found in my microwave system and my EME system, 4 to 10 dB of attenuation worked best between the last preamp and the IF radio in my setup. But I was using TS790, a very good radio, but it seemed to overload pretty easily and it needed some extra attenuation on the receive line. So if you're going to get measurements and only one of your buddies has got a distortion analyzer, get everybody together, get a whole bunch of radios and check them all and have kind of a receiver party. That's my advice. I think radio is always better when you do it with friends. It's just more fun. Okay, well, that's the whole thing on receiver improvement. I hope it bears looking at twice to kind of get some of the details out. But if you have any questions, you can email me at drzarko56@yahoo.com, and look forward to seeing you again on JEY Labs. Thanks very much. Bye.